Assalamualaikum, my name is Amir bin Kasmi. My metric number is B0822210550. I would like to introduce our group member is Yap Cik Gian, Profesor Sina, anak Nawan, Dewan Raj, anak lelaki si Baragu. And thank you to our Madam Rosnaini binti Ramli, and to our fellow friend. Before we start our presentation, I would like to introduce to you all our agenda have 5 parts. For part 1 is introduction, the second one is methodology, the third one is method analysis and result on item 1B and 1C, the fourth one is discussion, and the lastly is conclusion. Introduction. In advanced electrical circuit, transfer function play a vital role in analyzing and understanding the system behavior. A transfer function relates the input and output in linear time invariant system, typically represented as ratio of polynomial in complex variable S, where S is the Laplace variable. The transfer function provides valuable information about how a circuit or system responds to different input signals in the frequency domain. By examining the transfer function, engineer can gain insight into key system properties such as stability, frequency response, and damping. Transfer functions are commonly used in various applications, like example including control system, signal processing, and circuit analysis. They enable engineers to design and optimize circuit by predicting and manipulating their behavior. By mathematically modeling a circuit using transfer function, engineer can simulate and analyze its performance before implementation, saving time and resources. To obtain the transfer function of an electrical circuit, several techniques can be employed depending on the circuit complexity. For simple circuit, techniques like circuit reduction, nodal analysis, or mesh analysis can be used to derive the transfer function. This method involves applying Kirchhoff's law and solving equations to express the circuit response as a transfer function.
Good morning to Madam Rosani and my fellow friends. My name is Yap Chi Gian, and I'm from Beei S1 and my matrix number is B0822102278. So the second part is about the methodology, and I will present about it. In methodology, they have 2 parts. The first part is converting transfer function to BODE plot, and the second part is converting BODE plot to transfer function. So in the first part, the first step that we need to do is obtain the transfer function. The second step is simplify, derive, and turn into standard form. Third step, calculate magnitude and phase for BODE plot. The fourth step, identify the zero and poles. And the last one is draw BODE plot. And for the second part, the first step that we need to do is examine the magnitude of the BODE plot. Second, find the corner frequency. Third step, determine the DC gain. And fourth step, identify the zero and poles frequencies. And the last part is the construct transfer functions. So for the third slide, I will present about the method analysis and result on item 1B. So in this slide, we already mentioned earlier in methodology, the first part is converting the transfer functions to BODE plot. So as you can see in the left hand side of the slide is the equations of the transfer function that we need to do and calculate. And after that, we will refer the equation that we have calculated and write it, and then sketch the BODE plot graph as you can see in the right hand side here. So let us see the questions they have given. So first the question is given is the 200 omega over bracket omega plus 2 bracket omega plus 10. After that, we need to do a step-by-step equations. As you can see in below here is the step of the equation that transfer to standard equation. So at the end, we will get the standard equation, which is the 10 omega over bracket 1 plus omega 2 bracket 1 plus omega 10. So after this, we need to rewrite in the magnetic pole, which is HDB equals to 20 log 10 plus 20 log omega minus 20 log 1 plus omega over 2 minus 20 log 1 plus omega 10. So after writing the magnetic pole of the equations, we can now start to sketch our BODE plot graph. So as you can see in the first of the 20 log 10, within these equations, we can using our calculator, using our calculator to calculate the value of the 20 log 10. So the value that we get is 20 dB. So as you can see in the right hand side of the graph, the orange line refer to the 20 dB. And we all know that the 20 log 10 is the constant term in the BODE plot. That's why we will draw a line, a constant line in the 20, as you can see in the orange line, and then label as a 20 log 10. So after this, we will see the second equation, which is 20 log omega. And we all know that the 20 log omega is the 0 at the origin. Why? Because as you can see in the second equation, the omega is upper side of it, so that's why it's the 0 at the origin. And we will sketch the graph, sketch the plot, and then as you can see, the green line here is the starting point from negative 20 dash the frequency of 1 until infinity. And this green line is represents the 20 log omega. So after this, we will see the next, which is the negative 20 log 1 plus omega 2. And within this equation, we know that it's a simple pole. And after that, we can simplify simply to draw our plot. So as you can see in the blue line, is referred to the equation of the negative 20 log 1 plus omega 2. And then this line is become low pass since it's negative. That's why the starting point is from 2, the frequency of 2, and then go down the low pass until can call it infinity. Also can stop at the any point of below here, below the line. So for the fourth one, which is the last equation, negative 20 log 1 plus omega 10 is same as the previous one, which is negative 20 log 1 plus omega 2. These two things is the same, also called simple pole. And as you can see, the right hand side of the graph, the red line is represents the negative 20 log 1 plus omega 10. And it's the same thing, also starting point from 10 and become go to the low pass, which is straight down until infinity. Also, we can stop at any point below the point. So after sketching the dot line, which is the orange line, green line, blue line, and the red line is represent also called is dot line. For this, we will draw the resultant line, which is shown in the black line in here. So at first, we can see from 0 until 2, we can find out that the dot line is attached is the orange one and the green one. So we all know that the orange line is the constant term, although it's 20 dB, but it's not affected to draw our resultant line. That's why we will see the green line here, and the green line here is going upper until infinity. That's why the dB that is to draw the resultant line is plus 20 dB. And so as you can see, we will starting at 0 until the upper of the 2. So upper of the 2, and then as you can see, there has the gap between the black line and the orange line. And here, this is the gap we all know that is coming from the blue line in here, which is dash it, and then we all can consider the black line from 0 until the second frequency stop at the point I draw here. So after this, we can see the black line here is constant line. Why? Because when we do the black line in the constant line, because we refer to frequency from 2 until 10, and then we all know that when we draw the black line in the starting point in upper here, the line is 20 dB. But instead of do it to constant, which is 0, we need to minus 20 dB. That's why 20 minus 20 is equals to 0, which is constant line. And to do that, we need to using the blue line, which is negative 20, and then the green line is 20, and then 20, the green line, the 20, sorry. So the green line is represent 20 minus the blue line of the negative 20, and at the end we will get 0, which is the constant line that we draw from starting point 2 until 10 here. So after that, the dot line that we haven't calculated is the red line. So as you can see from the graph of the dot line, the red line is become low pass, which is straight down, and we can so within that we can consider, we also can say we already can draw it from the 10 point in here. After we draw the second frequency, the constant line, from here we can straight down until also can call infinity. Also you can stop at any point of the low pass at that. So that's the way to draw the resultant line. So as you can see in the book plot semi-log paper, I already written the 20 dB decade in the first here, and then in the constant line is 0 dB because, as I said before, the green line is represent 20 minus the blue line negative 20 becomes 0, and then straight down is the negative 20 dB, just like I mentioned the 20 in here, and then go downstairs in until infinity or stop at any point. So next step, we will draw the phase block. As you can see, the right hand side shows the semi-log paper is showing the drawing of the phase block, and the left hand side shows the equations that can help us to draw the phase block. So before we drawing the final resultant line, we need to draw the dot line first, which is the green line, orange, blue, and red, and consider as a dot line that can help us to draw the final resultant line of the black line, as you can see in the right of the graph here. So let us see the equations from the left hand side first. So from the left hand side of the equations that I already written, for the phase is equal to 90 degree minus inverse tangent omega over 2 minus inverse tangent omega over 10. And the two corner frequency is at the frequencies 2 and 10. And then we will see the first step, which is 20 log 10, and then you change to phase is equals to 0 degree. And for the second, which is 20 log omega, the phase is equals to 90 degree. And for the third one is the negative 20 log 1 plus omega over 2. And when we turning into the phase, we need to do the P1, as you can see at right, is equals to 2, because the J omega over 2, the 2 is the P1. Then the P1 is equals to 2, and P1 over 10 is 0.2, 10 P1 is 20. So this is considered as a frequency that we had to draw from 2 decades. Why I say that? Because as you can see, from 0.2 until 2 is 1 decade, 2 until 20 is 1 decade or so. And then we all know that if 0.2 until 20 is 2 decades. And for the fourth is also negative 20 log 1 plus omega 10. And we changing the phase is the phase P2 is equals to 10. And for 10 over P2 is 1. 10 multiplied P2 is 100. So let us see the first that we have changed it of the phase of the equations equals to 0 degree. As you can see in the orange line shows the 0 degree, which is K as the constant term. And the second is phase is 90 degree. And as you can see in the green line, is refer from the second part of the equations is constant also, because 90 degree constant. That's why it's drawing the constant line, the semi-log paper. So for the third one has a difference, because as I say before, we do the phase, we need to turn in the phase P1 equal to 2, P1 over 10 is 0.2, and this refers to 2 decades. So as you can see in the blue line here, the dot line is represents the third equation that I already write in the left hand side. And starting point is from 0.2 until 1 decade is until 2 in around here, and then until 20. So we also can say that starting point from 0.2 and the end point is 20. And we all know that the negative 20 also can turn into phase is negative 90 degrees, so low pass. So as you can see, the blue line in the diagram is showing low pass, which is until negative 90 degree, and then after that will become constant. So for the third equation is same as the third one that I have explained before, and the starting point is from 1 until 100 at the end point. So that's why the red line represents the fourth equations that I have right in the left hand side of the equations, and then the one will go until 10, and then will until the negative 90 degree, and then become constant back. So after drawing all the dot lines, we can now do the resultant line of the final line. So as you can see, from 0 to 0, sorry, it's 0.1 until 0.2. There has not considered any dot line, so that's why the red line is constant, and then starting from 0 until 0.2 is constant line. And then as you can see, after that we'll straight down like almost 45 degree. Is because as you can see when we attach that, the 0.2 until 1, the gap between the below here, below the gap, is considered as the gap below the negative, sorry, it's below the green line below here. That's why the line will become straight down like that. So after that, we will see the frequency line from 1 until 100. So as you can see, the dot line from the red dot line is low pass until negative 90. That's why the line from the black line here will until almost attach the red line, as you can see here. And then after that will become 45 degree back to the hundreds, and then become constant. So that is the way to draw the final resultant line. So before draw the final resultant, we need to consider the dot line first, which is the green, orange, blue, and red line. To draw that first, and then finally we can consider the final resultant line to draw it.
Hi, my name is Devendras Analaki Sivagaru and my matrix number is B0822100007 and my class is BEEI S1/S1. Today I'd like to present our assignment. Now I'm going to present the method analysis results on item 1C, and as we can see this is our word plot. Firstly, I like to explain how to form a transfer function equation from both plot graph. Firstly, we must identify the corner frequency and pole. Here we can see the corner frequency is omega equals to 5, 10, 100 radians per second. Here, then this is the results, the data, negative 40 and plus 20 dB. And then secondly, we must know the basic formula of standard transfer function. This is the transfer function formula. K equals to constant. So we must know the slope is increased. When the slope is increased by 20 dB, 0 is present. While will decrease, which is negative 20 dB with that, the pole is present. We know that omega equals to 5 per radian second is 1 plus omega over 5, and omega equals to 10 radius is 1 plus omega over 10 in pole. And lastly, we know that the omega equals to 100 per radian second is 1 plus omega over 100 square in pole. And the standard transfer function formula, this is the transfer function formula, and constant times with 1 plus j omega over 5 here over 1 plus j omega over 10 times with 1 plus j omega 100 square root. Then we must input the data from board, and we must know the 20 log constant equals to 20. The 20, this is the 20 from here because the starting point 20. So 20 log constant equals to 20 and log constant equals to 1, k constant, the last answer is constant equals to the 10. And after that we must times in properly, and you know that the constant times with 1 over 5 times with j omega plus 5 divided by 1 over 10 100,000 times with j omega plus 10 times j omega plus 100 square. Then we calculate step by step, and then we get the last answer for the standard transfer function for this method. Thank you.
Hello, my name is Efisosina Danaon. My matrix number is B0822100042. Today I would like to present my part, which is discussion. Transfer function to word plot. Firstly is transfer function analysis. Complex variables are used to express transfer functions, usually in a Laplace domain. They offer an accessible mathematical rendering of the system. In the Laplace variable, the transfer function is typically expressed as a ratio of polynomials, such as h equal to n over d, where n and d are both polynomials. We may deduct the system's stability, transient responsiveness, and steady-state behavior by looking at the poles and zeros to the transfer function. Second is BODE plot construction. The magnitude plot and the phase plot are the two components of the BODE plot, which is a logarithm display. We replace S with J, where J is the imaginary unit that is the frequency. In the transfer function, S assess the magnitude of resulting complex number at various frequencies to produce the magnitude plot. By calculating the phase angle of the complex number at various frequencies, the phase plot is produced. With frequency on the x-axis, the magnitude in decibel, or phase angle in degree on the y-axis. Both graphs are commonly displayed on logarit scales. The third one is BODE plot interpretation. We can better grasp the system gain characteristic at various frequency. Thanks to the magnitude display, it offers detail about signal amplification or attenuation. The phase plot explains the phase shift that the system introduced to input signals at various frequencies. BODE plots are particularly helpful for building filter, figuring out system bandwidth, and evaluating stability. BODE plot to transfer functions. BODE plot analysis. In order to identify the order of the transfer function and the existence of any zeros or poles, we analyze a BODE plot by looking at the slope and intercept of the magnitude plot. We also look at the phase plot to determine the features, the phase shift, and the existence of any extra poles or zeros. Transfer function reconstruct. We recreate the transfer function using a detail from BODE plot. We can find the gain constant at the position of the poles and zeros using the magnitude plot. The phase plot reveals information about the phase shift brought on by poles and zeros. We can translate the transfer function into a ratio of polynomials by combining this result. Model refinement. It's crucial to remember that a BODE plot reconstruction transfer function might not be entirely unique. To improve the model, further data and hypotheses can be needed. The transient response and stability margin can potentially need to be analyzed independently because the BODE plot alone only provides limited information about them. For the summary, we can see the system frequency response by converting a transfer function to a BODE plot, and we can create a mathematical model by converting a BODE plot to a transfer function. For the objective of system analysis, design, and control, both techniques are useful.
The conclusion that our group get from this assignment is, what have we learned is, what is the transfer function, what's the mean of transfer function, and what's the mean of BODE plot. And we know we and from and we know from the equation of transfer function we can get the point of magnitude plot and phase plot. From the point for magnitude plot and phase plot, from the point we can draw the BODE plot by referring that point of magnitude plot and phase plot. By referring the point of magnitude plot, we can draw the BODE plot. And from BODE plot graph, we can get the standard equation of transfer function by referring the value of corner frequency by using and solving by solving the equation by using all step function. What we have achieved from this assignment is we get solve the transfer function equation. We get plotted BODE plot from result of magnitude plot and phase plot. Lastly, what we achieve is we get identify the location of zero and pole from BODE plot graph. Finally, from this explanation, our group hope that to be able to give some knowledge about how to solve the transfer function equation and how to assign and draw a BODE plot, and from the BODE plot how to get the standard transfer function. And we hope we can get to help our friend to understand our explanation about this topic. Thank you.